It happens in millions of kitchens every night. You make pasta, you make sauce, you toss them together, and 5 seconds later, the sauce slides off the noodles, pools at the bottom of the bowl, and leaves a sad tangle of dry pasta. Meanwhile, at any half-decent restaurant, those exact same noodles come out glistening. Every single strand is glued into a thin, uniform jacket of sauce. The difference isn't a matter of seasoning or better olive oil. It is a difference in how the liquid behaves at a molecular level. For decades, home cooks have been taught one universal rule: cook your pasta in a massive volume of heavily salted water, usually about 4 liters of water for every 100 grams of pasta. There is a mathematical flaw hidden in this ratio that makes a stable sauce almost physically impossible to achieve. Building a sauce that actually clings requires crossing a highly specific starch concentration threshold. And if we look at the fluid dynamics of a hot pan, we can see exactly why the traditional boiling method is engineered to fail. Every pan of sauce starts with a core chemical tension. You have water, from tomatoes, wine, or cream, which is polar, and you have fat, like olive oil or butter, which is nonpolar. Because these two molecular groups refuse to share space, heating them up together without an intermediary results in rapid, inevitable separation. To force oil and water to stay together, you need a third ingredient. You need an emulsifier, a molecule with dual polarities that acts like a tiny diplomat, bridging the boundary layer between the two liquids. In a pan of pasta, that emulsifier comes from exactly one place: the starch that leaches out of the wheat as it hydrates and swells in boiling water. That cloudy pasta water you usually pour straight down the drain provides the structural glue required to build your sauce. The starch leached into the water consists of 2 distinct polymer types, each performing a different structural job in the pan. Amylose is a linear glucose polymer. Above 60 degrees, these chains unzip, trapping water in a 3D network. This raises viscosity 2.4 times and coats fat droplets, preventing coalescing. Amylopectin is heavily branched. It swells outward, providing dense physical mass and rich mouthfeel. Working together, the tangled network of amylose and the physical mass of amylopectin suspend those lipid droplets to manufacture an opaque, creamy liquid that clings to the pan. In early 2025, physicists published a paper in Physics of Fluids analyzing the phase behavior of a notoriously unstable sauce, cacio e pepe. They built a fluid dynamics model by testing different combinations of starch, water, and cheese across a range of temperatures to see exactly how the sauce reacted. This diagram maps starch against protein mass fraction, revealing a strict threshold at 1%. Below this line, the sauce fails. Cheese proteins seize into the mozzarella phase, total separation. The mathematical optimum for stability sits safely between 2 and 3% starch concentration. Hitting that 2% starch mark isn't a culinary preference. It is an objective physical requirement to keep those proteins separated and perfectly suspended. Now, let's look back at the universally taught home cooking rule: boiling 100 grams of pasta in 4 liters of water. If we calculate the mathematical reality of that volume, the maximum starch that leaches out is diluted down to roughly 0.3%. At 0.3%, you are nowhere near the stable zone on the phase diagram. Standard pasta box instructions permanently strand you deep in the failure zone. Restaurant kitchens operate completely differently. They use highly restricted water volumes, or they reuse the same water for multiple batches throughout a busy dinner service. The chef's sauce clings perfectly to the noodle because their solvent concentration is 6 to 10 times starchier than yours. The scientifically optimized parameter for your home kitchen is simple: reduce your boiling water to 1 liter or less per 100 grams of pasta. Restricting the volume of the solvent artificially elevates the residual starch concentration in the pot well past that vital 2% safety threshold. But having starchy water is only half the equation. The final required phase is pan finishing. You have to pull the pasta out about a minute before it is fully cooked and drop those wet, dripping noodles directly into the sauce. Here you introduce mechanical shear. 60 to 90 seconds of violent tossing physically shatters the pooling lipids into microscopic droplets. That intense agitation forces the amylose network to bridge those newly multiplied boundary layers, locking the emulsion in place. While you toss, a critical secondary dynamic occurs: osmotic absorption by the hydrating wheat. According to 2024 research in Frontiers in Food Science and Technology, the noodles gain up to 2.6 times their dry weight by drawing the surrounding emulsified liquid directly into their internal starch matrix. Mechanical shear and osmotic absorption work together to ensure the sauce acts as a bonded structural component of the noodle, rather than a separate liquid sliding off the surface. Before trying this, there are 2 final guardrails. First, skip the oil in your boiling water. Adding oil to the pot physically alters the noodle surface, making it slightly hydrophobic. It actively repels the emulsion from adhering later on. Second, respect the thermal limits. If you are adding cheese, the proteins will seize immediately if introduced to direct heat exceeding 70 degrees Celsius. Pull the pan off the heat source first. The residual thermal energy is enough to gently melt the proteins into the starch matrix without triggering a mozzarella collapse. A glossy, perfect sauce is just the predictable result of engineering your phase chemistry and solvent concentration correctly.